Yes. Well, hi Nate, hi Brianna. This is our live Zoom session of the week. You guys have any questions before I get started on this stuff?
Yeah, like how are we gonna use ketones and aldehydes? Like I was doing the reading and stuff, like with the properties and stuff. Like how do we use them?
Yeah, pretty much we reviewed their properties, the way what their structures look like. The use is in these reactions. And we're really only looking at two different kinds of reactions, or two or three different kinds of reactions. So there was adding hydrogen to aldehydes and ketones, which we call reduction. And then there's adding oxygen groups or a nitrogen group or, and mainly that stuff. And then at the very end of today, I'll show just real briefly how you can add a carbon to a aldehyde or ketone. So really the answer to your question is that aldehydes and ketones can be reacted with a lot of different things to create new molecules or to synthesize molecules from nature that exist in nature. So, and a lot of those might be medicines or compounds used for agriculture or all kinds of things. The tie-in with the health sciences is that a lot of, all drugs are organic compounds for the most part. And they're interacting with organic compounds in the way they work. And as far as all those reactions go, I'm basically gonna start off where we left off, just showing again the reduction reaction here. So hopefully you can see the screen sharing. So this was, after covering the aldehydes and ketones, what they look like, sort of their simple names, and how they tend to react. We saw the reduction reaction, which takes place like this. So here's an aldehyde. These are the reduction conditions. When you see lithium aluminum hydride or sodium borohydride, you can think of it as like a hydride delivery system. Hydride delivery. And we have the word nucleophile as something that can form a new bond using electrons to a carbonyl carbon. Remember, there's a carbon there of an aldehyde or ketone. And a hydride is the simplest nucleophile, just a hydrogen with a minus charge. So that's this hydrogen that got added. The second step here is just simply protonating or adding a hydrogen on to the oxygen. So that hydrogen comes from water, most likely, as the reaction is quenched, as we say, or completed by adding water. It kind of tends to stop all other reactions that are going on as well. So in the last video, I went through the step-by-step mechanism of this, so I don't really need to go over that again. But that was just a reminder of what the addition of hydride nucleophile is. So the way we're marching through this is like, what about other nucleophiles that do basically the same thing? So again, you're looking at an aldehyde that has the same kind of reactivity. You're looking at electrons from an oxygen that can form a bond to the carbonyl carbon. And the bond it's forming is this bond right here on the right. And it's displacing electrons onto the oxygen here. And these arrows show the same exact bonds forming and bonds breaking as what's happening above with the hydride addition. So there's really almost no difference between that reaction and this reaction, except that you're adding an oxygen nucleophile here. The thing that's forming the bond is the nucleophile, and you're adding a hydride nucleophile above. But otherwise, it's the same thing. The result of these arrows will be initially, I can draw it down here, that this oxygen now has extra electrons and a negative charge. This hydrogen's still here, and the OH is attached via that new bond. This just completes in that last, finalizing step where it just adds a proton like that. So it's forming a bond to that hydrogen proton. That bond breaks. And so, we've added that hydrogen, and the oxygen is now no longer negative. So really in the end, if you see, you can I don't like the word memorize, and I'll tell you why, but you can memorize the net reaction if you recognize the aldehyde here and recognize that it is ending up like this if you're subjecting it to these conditions. So you can memorize those components of it and get these missing pieces, but understanding how it works helps remember it a lot better. And the other thing about that is a lot of people, if they memorize something like this, are going to do it very visually. They're going to memorize all of this, if you can see what I'm circling, all of this. But what happens when they see the same exact reaction, really, except a whole bunch of different atoms here, or maybe even on the other side of the carbonyl group? If they're just memorizing completely visually, like I've just got to memorize this, and not understanding how this works, they're not going to recognize it when they see this exact same reaction with different groups attached over here. For me, personally, that's just way too much to memorize, to try to memorize, because the number of groups that could be on either side of the carbonyl is literally infinite. It is truly, you can truly create an infinite number of structures on both sides of that carbonyl. So, so I really advise against always memorizing as a strategy. But you can certainly remember the components. You see the aldehyde here. You see it turns into, the aldehyde's gone, and you've got two OH groups on there instead, if you add an OH nucleophile. Okay, so you can also do, and again, you're going to see that in this reaction, starting with the same starting material, it's going to be with nitrogen as a nucleophile, but otherwise it's going to be exactly the same thing again. And so someone that learned the above mechanisms of how the hydride works and how the OH works as a nucleophile, at this point could probably figure out that the amine is going to do the exact same thing. It's going to form a bond, break this bond. The amine nitrogen has an extra pair of electrons on it. The new bond it's forming is right here. And you can almost visualize the same series of steps, right? The O becomes minus, picks up a hydrogen from water, and makes an OH group. So, but I can draw that out again. So the result of this bond forming and this bond breaking, again, is going to be O minus, that hydrogen is still there, and the new bond to NH3. However, this ends up with a plus charge because it's lost electrons in the bond forming. So it's not quite exactly one more step to the final product. It's actually two more steps. So, but they're trivial because all it is it gets a hydrogen, and that step is exactly the same. But to break it out one by one, now you have the OH and a neutral oxygen. That hydrogen's still there. You still have the NH3, but I'm going to draw it out so that we can see more what's going on here. You think about it, OH and NH is pretty similar. Hydrogen's stuck onto those kinds of atoms. This is a plus charge at this point still. So the water, or OH of water, excuse me, water or the OH that's formed here briefly, either one can remove, keep my arrows consistent, can remove one of these protons. Electrons go toward the plus charge. That gets you to the final product. So essentially, if you remember that you gain a hydrogen on the oxygen and you lose a hydrogen on the nitrogen to end up with the final product, you could abbreviate all of this part just by going, say, arrow minus, oh, sorry, plus H plus minus H plus. Plus a proton minus a proton, plus a proton on the oxygen, minus a proton on the nitrogen. You can sort of summarize it all in one step. Most chemists would realize quickly, like, oh yeah, I see what's going on, you know, like without having to do all these steps every single time. Again, you can recognize the exact same components, the aldehyde or ketone, the nucleophile that's being added that's forming the new bond to it, and it's going to be stuck on there. And then what the product of that eventually looks like after all the simple adding and subtracting hydrogens. There is, I will make another point because I'm skimming over another thing, which is exactly how these plus and minus charges form. At this point, it sort of should be apparent that when charges form, they don't like to just sit around. They tend to react into a final form that's not charged. So charged species are more reactive. And the question maybe is that, you know, exactly how does oxygen go from not being charged here on the aldehyde to being charged here? And there's a way to easily calculate that. But I'm not gonna go into it too much. It's called calculation of formal charge. Just briefly to show you an example, this oxygen actually has 2 lone pairs on it, while this oxygen actually ends up having a 3rd lone pair because a pair of electrons from here is moving up onto the oxygen. So, and by looking at the periodic table, we can easily figure that this has an extra electron, and so it's negatively charged, basically, because electrons are negatively charged. And if it's deficient in electrons, it's positively charged. Just thought I'd mention that. So that's almost all the reactions for this unit, except one more type that I'll throw in at the end here, and then show more of in the last video. So this will be review, actually, just more examples of the same kind of thing. So here's a ketone in this case with an oxygen nucleophile, OH, bond forming, bond breaking. Visualize the oxygen picking up a hydrogen from water at the end, and you can easily draw the product being, oh, yep, the oxygen becomes an alcohol. The OH group has added before that. Here's the new bond. That's it. And notice that all of this is just spectating. It's just not involved, really. It just stays the same throughout the course of the reaction. And again, we've gone through the step-by-step part where we could draw what happens to this and then how it picks up a hydrogen to get to this. But we've already done that now a couple of times. Here's an example of another nitrogen nucleophile and a ketone. And so you look at this and you say, well, I'm not sure what the deal is with all of this, but it sure looks a lot like, it reminds me a lot of this. It's basically looks the same. So I propose that it's gonna do the same thing, and that would be correct to propose that. It's gonna form a new bond from nitrogen to the carbonyl carbon. The oxygen's gonna get negative, then it's gonna pick up a hydrogen, and so we can draw the final product right away. The O becomes an OH. All of this part is still hanging on, and our new bond to nitrogen. And if it works the same way as this one did, we remember that it loses a hydrogen at the end also, in the same way that the oxygen gains a hydrogen. But then this will still be on there, CH2. And so that's our final product. And really, again, if you were just memorizing, you would say, well, I know what this is, but I don't know what this does. It looks different, and so I haven't memorized this, and so I don't know what it's going to do. But if you realize that it's basically the same kind of structure with electrons that can form a bond, in other words, a nucleophile, an amine nucleophile, then you can easily see that this is going to occur in the exact same way as it did with this. So we've got things that we can vary on both ends. We can vary these groups, and we can vary things like this that are attached to the nitrogen. When you do enough practice of practice problems like this, it really doesn't take that long before you start to see like, oh, this is the same as that one. Oh, yep, this is the same as the other one before. Oh yeah, and this one's the same too. So, but that's the point of doing the practices. Any questions on any of that so far? We did hydride addition, OH addition, and amine addition. We kind of realized those are all the same, basically, with a few little differences in how it picks up protons at the end or loses them. And then we saw some more examples. So any questions before I go to the next thing? Or things you'd like to see redone or anything? Okay. So having done the sequences from start to finish, it becomes then likely that you should be able to fill in missing parts. So if you're presented with a problem like this, having done a bunch of the practice of what we did above, you would see the final product here and recognize that it probably came from a carbonyl group here where an OH group was added to it, because this is what we see at the end of those every single time. But you're not just given that, you're given the step-by-step. So working our way backwards, or just sort of looking over the whole thing, right? It's all the steps. So you could recognize that to get to this final one, you remember from the forward reaction that the last thing is just adding a hydrogen from water. And so you say, oh yeah, what's added at the end is just water for this to go and grab a hydrogen from. And then you say, oh, and I remember how we got to this. We got to this by adding an OH minus, which is given, to a ketone. So the rest is just filling in what doesn't change. And then the ketone is here. And so you remember like, oh yeah, that forms a bond and that bond breaks. Again, same, so it's very much college level type of thinking where you process, then start to be able to fill in missing components given that same process, because you've learned it and practiced it. And really the third step in that logical progression would be like, given this last final thing, how do you make it? Here's this, how do you make it? Not with all the other clues, This kind of logical process is all of higher learning. It's not just organic chemistry. It's like, here's some thing with a bunch of components. Can you fill in the missing components? Can you get to the result or some new result ultimately without all the other stuff, clues ahead of time? Here's another one with just missing parts. So like, it's something we've learned already. We have the starting material, a ketone. It's reacting with something to give something. And then water is added to that. And then you get to this. And so then you see, oh yeah, I've done enough of these. We added a nitrogen group to a carbonyl to get to this. The amine nucleophile example. So I'm going to say NH3 here, like our very first one of these. You can put lone pairs there to remind yourself that they're there to create a bond to the carbonyl carbon, exactly the same as above. That gets us to here. NH3, and I guess there's the whole business with this being charged, and this so the oxygen has to gain a hydrogen, the nitrogen has to lose a hydrogen, and without having to draw those out every single time, I said you can go plus H plus, minus H plus. Water is going to probably help govern that, and then you get to your final product. So no need to do the whole thing every time. The adding and removing hydrogens is pretty trivial reaction. Okay, so the last two were just fill in the missing pieces of really reactions that we saw before, and literally the only difference was what was attached to the functional group. Think about that word functional group, that phrase. It's like the group that functions, the group that has a function, not the group that's just spectating. So, you see oxygens, nitrogens, sulfurs, double bonds, triple bonds. Those are functional groups. That is where your attention probably should be drawn to. All the hydrocarbon groups, CHs, CH3s, CH2s, pretty much, not easy to react. Very stable, actually. The one type of CHs of hydrocarbon parts that can react only really do so because they're close to a functional group, like right next to a functional group. We study that in regular organic chemistry. So anyway, that was all filling in missing components of reactions that we've studied. Finally, putting all the concepts together. How dare I do such a thing? No, I'm just kidding. We do learn all these things one by one, and then we move on to the next thing, often without really like showing how they all could fit together in the science of organic chemistry. So I don't know if you noticed, as I've been scrolling down, we had some pictures on the side here. There's that one there. This one here. Very obvious, right? Those were all pieces. Now, when you put them all together, it has a whole lot more meaning. Separately, it's like, oh, I kind of recognize what that is. Put it all together is when it takes on the actual full meaning. So any science, any human endeavor that's composed of parts, which is basically all of them, I'm getting real philosophical today. You know, it's the same deal. At some point, you need the ideas that you're going to be able to put these parts together. So, and I think I will be finishing earlier today because this won't take that long. I put together a sequence that uses a lot of the chemistry we've been doing recently. So here's a ketone. I'm sorry, an aldehyde, right? Here's our two-step add a hydride reduction. The first reagent adds H- to the aldehyde, and then the second part protonates the oxygen and provides that hydrogen. So we've got our new bond from the hydride. The oxygen picks up a hydrogen from water in the second step, so step 1, step 2. And now we've got this. Okay. From here, we had that older, before this unit reaction, of where a base can remove a hydrogen like this. So in a way, I could have skipped step 2 possibly, because it brings me back to this. But I just wanted to remind folks that you can remove that hydrogen with a base from an alcohol or a phenol, was how we saw it before. I think it was on the last quiz. Last question on the last quiz. Okay, now we're back to this guy. This can behave very much like the OH as an oxygen nucleophile. So in these first steps, I took an aldehyde and made an oxygen nucleophile out of it. And I say it behaves very much like the OH did above in the 2 examples I showed. Not very much like it. It behaves exactly like it. Forms a bond, kicks these electrons up. There's the bond that it formed. And so it's really exactly the same reaction as above. Then protonation of that to become this alcohol, and we've created this. And to continue to put in stuff from recent units, oops, I'm missing a double bond here, got lost along the way. There it is there. I recognize now that, so I step back, I take the bird's eye view, I look over the thing and I say to myself, oh wait, this is a chiral center. This is a chiral molecule. This exists in 2 forms, one of which is going to be R and one of which is going to be S. So that whole unit, that stuff doesn't just exist in a vacuum. It's tied in directly with synthetic organic chemistry. The point at which this chiral center is created you have to sort of go back. It's already here in the previous step. Here's where it gets created. This oxygen is forming this bond. And then we remember from our earlier structure and bonding that this is flat and trigonal planar geometry. So there was questions with points on what is the geometry of this and this and this. Once those points were assigned or not assigned, we weren't done with it. Here it is again. So this bond can form from either the top face or the bottom face of the carbonyl. Can form to either face of the molecule. Squeezing this in here. And so because it can form with equal likelihood to either face of the molecule, since it's flat, there's no preference. Both sides look the same to this oxygen nucleophile as it's floating in. And so that's why you get both enantiomers. So we're going to expect that one version is going to have the OH pointing up while this new bond was formed on the underside or the backside, I guess, as we're looking at it. And then you're going to have another version where the OH is back and the new bond had formed from coming in on the top face or on this side of it. These are mirror images. They're enantiomers like we saw in the last unit. And so we can use this opportunity to review how do we assign R and S, because some people get those wrong. And then, so we can review a little bit of that. We've got the time. These are the chiral centers right there. They're carbons with 4 different things attached to them. So this carbon has you go atom by atom. So this carbon has an oxygen here, oxygen, carbon, carbon. But if you have to keep going out to check to see if those are actually different. Like the 2 oxygens, are they different from each other if you keep going out? It's like, oh yeah. This oxygen is attached to hydrogen. This oxygen is attached to carbon. This carbon right here is attached to a hydrogen and another carbon. This carbon here is attached to 2 hydrogens and another carbon. And so, but we've learned all these rules of prioritizing these. So we could see right away both oxygens are going to be number 1 and number 2. And this is going to be number 1 because attached to this oxygen is a carbon, while attached to this oxygen is a hydrogen. So this one's number 2. This group is going to be 3 because in the way we count a carbon on a double bond, it's attached also to an imaginary carbon. So we learned that before, because it's attached to a double. So as in prioritizing these last 2 groups on these 2 sides, this carbon is attached to hydrogen, carbon, imaginary carbon, because it's double bond. This carbon is attached to hydrogen, hydrogen, carbon. So the 2 carbon side wins. It's all based on atomic number. So this is our group 4. And we didn't do many or any examples where group 4 was not pointing either toward us or away from us. In this case, it's pointing, it's in the plane of the screen, in the plane of the paper. so we have to visualize basically, and this is a tough one. So I'm not going to throw ones like this at you probably too often, but if you're looking at it, you have to imagine yourself looking at it in this direction, and with 4, that would put 4 pointing away from you. And 1 would be on your right, 2 would be on your left, coming toward us, and 3 below you, and 4 pointing away from you. So going from 1 to 2 to 3, as we look at it, imagining ourselves looking at it, we're actually in the plane of the screen. It's counterclockwise S. So that was a good one. I mean, it was a lot of work, but it was a good one for review. When you're doing the other one, everything's already done, right? This is group 1, group 2, group 3, group 4. You don't have to do all that again. You visualize again, if you can, that you're looking at it with 4 pointing away from you. From 1 to 2 to 3 is now clockwise, and so it's R. So just going back then, this whole problem just uses, I think, almost all the chemistry we learned in recently, except for the amine nucleophile. You've got the addition of the hydride nucleophile to the aldehyde. You've got a demonstration of how you can remove a hydrogen using a base to create this O-. We then use that as an oxygen nucleophile on a ketone to form the final product. And then we realize that that final product is chiral, exists in 2 forms that are enantiomers and mirror images. And then we assigned those just for review. So I just, I feel like it's good to see the whole plant once in a while. We won't do it that often, because we're just still learning the pieces, the plant parts. But I do I feel it's my responsibility to show the whole thing sometimes. So we are going to finish a little early. The last chemistry for this unit is the same chemistry again, basically. Same, only different, right? So this time it's a carbon nucleophile. And so H- hydride nucleophile, OH- oxygen nucleophile, amine nucleophiles, carbon nucleophile. Somehow you've created a carbon that has a negative charge like this. But imagining that if you can do this, then you can easily predict that it's going to do the exact same thing that our other nucleophiles do, which is form a bond as a nucleophile to the carbonyl carbon, forms a bond, kick electrons up, protonate. So we've created this new bond, and we've got an alcohol where the carbonyl was. Otherwise, isn't this exactly the same? I hope. If you're looking at this and you're saying this looks completely different, I've never seen anything like it, I would start to get worried. Because it really, if you substitute the abbreviation like NU for nucleophile and plug in H-, OH-, amine, there's a way to make those minus too, or carbon minus group, and you plug all those in for nucleophile, then you see that these are all the same reaction, actually. So, and then same like all the others, you can vary the groups on either side of the ketone or on the side of one side of the aldehyde. You can vary the groups attached to the nucleophilic carbon. So arguably you could create new carbon-carbon bonds like this one below to the aldehyde, what was the aldehyde. You can create new carbon-carbon bonds, and you could argue that that's actually the most important of all these reactions, because carbon bonds make up the frameworks of almost all organic compounds. I'm going to go ahead and say all organic compounds. So when compounds need to be synthesized as drugs or other products, the making of carbon-carbon bonds selectively is really the most important type of reaction there is. So that's why I felt it necessary to add this, but it also fits in with what I'm saying here, which is how do aldehydes and ketones react? What is the most important way that they react? And the answer is with nucleophiles of various types, and most importantly, probably with carbon nucleophiles. So that's how this all is part of the same thing. And fortunately, all of these react in almost exactly the same mechanism, with a few hydrogens popping on and off at the end. So should save this for now. So finishing a little early here, we're about 8 minutes early. Any questions? Okay, so also if anyone wants to set up an appointment or do anything like that, you could let me know now, or otherwise just email me. The quiz will be posted tomorrow.
I actually have like a really quick question.
Yeah.
So in the second fill in the blank part with the NH3 and the oxygen, is the oxygen taking the hydrogen from the water or from the NH3?
It's funny that you asked that, because I thought about showing that, because and maybe you're thinking the same thing I was thinking, which is if you draw out more, your NH3 kind of looks like this, right? So there, you could imagine that maybe this picks it up right there, and these electrons go down here, and then you get there all in one step. I think that can happen. I held off on showing this because it's different from everything we've been seeing so far. Or it could happen in 2 steps. So, you could protonate the oxygen first, which creates an OH minus from the rest of the water. Then the OH minus can go and grab one of these hydrogens in a second step to completion. But the reason I think that possibly this is more likely is because they're right next to each other. So when in the other scenario, you're waiting for things to float in and react. So while the OH is sort of floating toward this, the O minus can just go doink, grab that hydrogen. Too late, I've already got a hydrogen, and the nitrogen already lost a hydrogen. So I kind of do think that this is probably more likely, just in an internal exchange, because they're so tightly in there, close next to each other. If you build a model, especially, you can see it.
Well, thank you.
So that's a great question. Yeah, thank you. Okay. I guess I'm going to stop the recording then. And so this will be posted as usual. Look for the next quiz tomorrow, and probably a very short video. I'm gonna say late tonight on the carbon nucleophile thing. So, okay. And so thank you guys for coming. And oh, and by the way, I got my second vaccine dose today, so I don't know what kind of shape I'll be in tomorrow. I'm not planning anything for tomorrow. Maybe I'll be fine. Some people say the next day is pretty bad, so. Okay, stop the recording.